A journey to Mars, currently estimated at several months using existing technology, presents significant challenges. Extended exposure to cosmic radiation and the effects of prolonged microgravity pose substantial risks to astronaut health. These factors highlight the need for faster, safer travel options. NASA is actively pursuing alternative propulsion systems to dramatically reduce the time it takes to reach Mars. This necessitates a move beyond traditional chemical rockets, whose inherent limitations restrict long-duration missions. The prospect of significant time savings, potentially reducing the journey to weeks or even days, is a major driver of this research. A key element in addressing these issues is the development of nuclear thermal propulsion. This revolutionary approach, utilizing nuclear fission, promises to unlock vastly greater energy efficiency compared to chemical combustion. The potential benefits of nuclear thermal propulsion are immense, offering the possibility of dramatically shortening travel times and reducing the dangers of prolonged exposure to the harsh conditions of space. This pursuit of a faster and safer route to Mars is central to NASA's broader strategy for human exploration beyond Earth's orbit. Nuclear thermal propulsion, a game-changing technology, harnesses nuclear fission to generate thrust. This process uses uranium-235 as fuel, a key component in generating the energy needed for propulsion. Unlike chemical rockets that rely on combustion, nuclear thermal propulsion offers a significantly higher power density, making engines more compact and powerful. This translates into higher exhaust velocities, enabling rockets to accelerate more rapidly, ultimately reducing travel time. NASA's focus on higher temperatures and specialized fuels within the nuclear system is a key differentiator from conventional light water reactors, offering a compact design. This advanced technology has the potential to drastically improve mission durations and decrease the time required for deep space voyages. While the concept is not entirely new, advancements in materials science and reactor design promise to overcome past limitations and allow for more robust and efficient applications in space exploration. The development of this technology is crucial for ambitious future missions like crewed trips to Mars, as well as for extending human presence beyond Earth's immediate vicinity. NASA's Draco program, a key initiative in nuclear propulsion, plans to utilize low-enriched uranium (LEU) fuel in its first test missions. This choice aims to mitigate nuclear proliferation risks, a significant concern with highly enriched uranium. However, the lower enrichment level necessitates a larger fuel quantity for comparable energy output, potentially impacting overall mission weight. This challenge highlights the trade-offs inherent in pursuing advanced propulsion systems. The development of more efficient fuel utilization strategies and engine designs is vital to offsetting this added weight. Challenges also include the need for robust and reliable materials to withstand the extreme conditions within a nuclear reactor. The program's success hinges on demonstrating the viability of nuclear propulsion for missions into low Earth orbit. Beyond initial testing, the goal is to set performance benchmarks that match or surpass conventional chemical rockets. The eventual goal is to utilize this technology for deep space missions, including potential missions to Mars. DARPA's involvement emphasizes the program's strategic importance in pushing the boundaries of space travel. Successful development of nuclear thermal propulsion would revolutionize space travel, drastically reducing journey times to destinations like Mars. This technology's potential for significantly shorter transit times offers numerous benefits, including reduced astronaut exposure to harmful space radiation and microgravity. Beyond reduced travel times, the technology opens possibilities for more ambitious missions like extended deep space operations and potential human outposts beyond Earth. Applications extend beyond exploration, potentially impacting national security through faster maneuverability in cislunar space. This capability would offer strategic advantages in defense and commercial space operations. The implications of faster, more efficient space travel are far-reaching, impacting not only scientific discovery, but also potentially creating new economic opportunities and geopolitical considerations. Further advancements in reactor design, fuel efficiency, and propulsion optimization are crucial for fully realizing the transformative potential of nuclear thermal propulsion. The pursuit of this technology could usher in a new era of space exploration and human presence in the cosmos. The pulsed plasma rocket, PPR, represents a more advanced nuclear propulsion concept, offering a potentially simpler and more cost-effective approach than traditional nuclear thermal propulsion. This system utilizes controlled nuclear explosions to generate thrust, generating plasma bursts expelled through electromagnetic nozzles. This innovative technology aims to overcome limitations in both thrust and specific impulse, crucial factors for long-duration space travel. The potential for higher thrust and greater fuel efficiency suggests the PPR could be a game-changer for deep space missions. However, achieving the desired performance levels necessitates overcoming significant engineering challenges. Research is currently focused on neutronic studies and the development of advanced components. These studies seek to optimize the system's subcritical operation, minimizing energy consumption and safety risks. The success of the PPR hinges on overcoming these engineering obstacles and achieving a stable and efficient propulsion system. A breakthrough in this technology would potentially revolutionize long-duration space travel, enabling missions to Mars and beyond. Chemical rockets, the workhorses of space exploration, rely on the combustion of fuel and oxidizer. Two primary types exist, solid and liquid. SpaceX's Starship, a leading contender for deep space missions, employs the Raptor engine, designed to maximize thrust and efficiency. Crucially, the Raptor uses methane and liquid oxygen, differentiating it from traditional designs. This alternative fuel combination offers significant advancements in fuel efficiency and thrust compared to older systems. Starship, with its 39 Raptor engines, is the most powerful rocket built to date. However, chemical rockets are inherently limited by exhaust velocity. This constraint directly impacts the duration of long-distance missions. A journey to Mars, for instance, currently takes several months, presenting considerable challenges like extended exposure to cosmic radiation and prolonged microgravity, with potentially severe effects on astronaut health. These limitations underscore the need for more efficient propulsion systems, a crucial requirement for future deep space exploration and extended missions. The limitations of chemical rockets highlight the importance of the ongoing development of alternative propulsion systems, like nuclear thermal propulsion, as a potential pathway to reduce travel times and improve astronaut safety during deep space voyages. NASA's ongoing research and development into advanced propulsion systems, including nuclear thermal propulsion and pulsed plasma rockets, signify a pivotal moment in space exploration. These technologies promise significantly faster and more efficient travel to destinations like Mars, reducing risks associated with long-duration missions. The potential benefits are substantial, impacting both scientific discovery and national security. Faster travel times would facilitate extended human presence in space and enable more ambitious missions. However, significant engineering challenges remain in refining these technologies. Further advancements in reactor design, fuel efficiency, and propulsion optimization are crucial for realizing the full potential of these breakthroughs. The collaboration between government agencies, private industry, and leading research institutions underscores the commitment to pushing the boundaries of space travel. The future of space exploration hinges on overcoming these challenges. Revolutionary nuclear fuel could cut Mars travel time to just 45 days. Scientists have made a major breakthrough that could transform space travel, a new nuclear fuel capable of powering rockets to Mars in just 45 days. This cutting-edge propulsion technology, recently tested by General Atomics, withstood extreme temperatures inside a nuclear thermal rocket reactor, proving that deep space missions could soon be faster and more efficient than ever before. Could this innovation be the key to humanity's interplanetary future? A major breakthrough in nuclear propulsion could change the future of space travel, allowing rockets to reach Mars in just 45 days, compared to the current 6 to 7 months required by chemical propulsion. General Atomics Electromagnetic Systems, GAEMS, has successfully tested a new type of nuclear fuel that can withstand the extreme conditions of a nuclear thermal propulsion (NTP) reactor, bringing humanity one step closer to faster, more efficient deep space travel. The fuel was subjected to intense heat tests, simulating the extreme temperatures of a functioning nuclear rocket engine, and emerged intact and operational. This breakthrough could revolutionize interplanetary travel, making missions to Mars, the Moon, and beyond significantly more feasible, safe, and efficient. How nuclear thermal propulsion could transform spaceflight. Currently, space missions rely on chemical propulsion, a technology that has remained largely unchanged since the early days of the space race. While effective for launching spacecraft into orbit, chemical rockets are too slow and fuel-intensive for long-distance interplanetary travel. Nuclear thermal propulsion (NTP) offers a radical improvement. Instead of burning fuel in a combustion chamber, NTP works by using a nuclear reactor to heat a propellant, such as hydrogen, to extreme temperatures. The heated gas is then expelled through a nozzle, creating thrust far more efficiently than traditional chemical engines. For decades, scientists have theorized that nuclear rockets could dramatically cut travel times to Mars and other deep space destinations. Now, thanks to General Atomics' successful fuel trials, this technology is finally moving from theory to reality. Fuel that can withstand extreme temperatures. The key to nuclear propulsion is finding a fuel that can survive the extreme conditions inside a nuclear reactor without degrading. GAEMS has developed a compact nuclear fuel element that was tested at NASA's Marshall Space Flight Center, where it was subjected to temperatures of up to 4,220 degrees Fahrenheit, 2,326 degrees, equivalent to the conditions a nuclear rocket would experience during a boost maneuver in space. A faster path to Mars and beyond. NASA and the U.S. Defense Advanced Research Projects Agency, DARPA, are already investing in nuclear propulsion research, awarding Lockheed Martin a $499 million contract to develop the demonstration rocket for Agile Cislunar Operations, DRACO. This next-generation nuclear spacecraft could serve as a prototype for future Mars-bound missions. With nuclear propulsion, the timeline for a human mission to Mars could shrink from the current 6 to 7 months down to just 45 days. This would dramatically reduce risks associated with long-duration space travel, including radiation exposure. Shorter missions mean astronauts spend less time in deep space radiation environments, reducing their long-term health risks. Psychological strain. A shorter journey would lessen the mental stress on astronauts, making missions more manageable. Supply efficiency. With a faster trip, less food, water, and oxygen would be needed, reducing mission costs and logistical challenges. The success of these nuclear fuel tests marks a turning point in propulsion technology, pushing humanity closer to regular interplanetary travel. What comes next? The future of nuclear rockets. The next step for General Atomics and NASA is to continue refining the nuclear reactor designs and propulsion systems that will harness this powerful new fuel. With the development of small modular reactors and high-temperature materials, nuclear propulsion is poised to become a cornerstone of future space exploration. As research progresses, nuclear propulsion could be used for missions far beyond Mars, enabling faster exploration of the outer planets and their moons. With efficiency improvements, spacecraft could even reach the edges of the solar system in a fraction of the time currently required. This breakthrough could reshape human spaceflight in ways previously only imagined in science fiction. If nuclear-powered rockets do indeed become the standard, they could pave the way for permanent human settlements on Mars and beyond.